The dinosaurs did not vanish in one explosion. Their extinction began with 24 hours that permanently rewired the planet. Before impact, life occupied nearly every habitat. None of it could sense the mountain already approaching from space. The object was probably a carbon-rich asteroid, roughly 10 to 15 kilometers wide and moving at extraordinary speed. Its size was terrifying. But size was only half the weapon. The other half was velocity. It crossed roughly 20 kilometers every second. At that speed, an ocean becomes almost irrelevant. Its destination was a shallow tropical sea near Yucatan, a target that amplified the catastrophe. Below the sea lay carbonate and sulfur-bearing rocks, materials capable of turning impact energy into climate-changing dust and gases. Shocked crystals, glass droplets, crater rocks, and global sediments preserve the event, like damaged frames from a lost film. There was no warning system, no evacuation, and nowhere on Earth prepared for what was seconds away. The atmosphere barely slowed it. Air compressed ahead of the asteroid into a descending wall of incandescent plasma. Near Yucatan, the horizon brightened beyond sunrise. Animals had seconds between noticing the light and being overtaken by it. From the upper atmosphere to the surface took less time than a breath. Then the Cretaceous world changed forever. Contact released energy near 10 to the 23rd joules, far beyond every weapon humans have detonated. The asteroid did not remain intact. It and the seafloor were crushed, melted, and vaporized almost instantly. Crater geometry suggests a steep, oblique strike, an angle efficient at launching vaporized target rock into the atmosphere. Ordinary minerals became extraordinary evidence. Quartz deformed, sediment became glass, and ancient seabed entered the sky. Within the nearest region, survival was effectively impossible. Heat, pressure, debris, and wind arrived together. The explosion remained regional for only moments. Its fastest material was already climbing high enough to become a global disaster. The impact excavated a temporary cavity far deeper than the crater that would remain. Earth's crust opened like a wound. Before the crater finished forming, seismic energy was already racing through the body of the planet. Compressed crust rebounded upward. For a moment, solid rock rose like liquid inside a planetary splash. Gravity pulled the central uplift apart, spreading deep crust outward into Chicxulub's distinctive peak ring. Within minutes, the collapsing structure produced a crater nearly 200 kilometers across. The visible crater was only the surface expression. Beneath it, the crust was shattered, heated, displaced, and made permeable. An ejecta curtain expanded outward. Large fragments fell nearby, while faster dust and droplets began crossing continents. Near Yucatan, enormous blocks returned first, striking land and sea while the main blast still expanded. Higher in the plume, vaporized rock cooled into glass droplets that became a worldwide impact signature. The sea had been thrown outward. Gravity now drew a chaotic wall of water and debris back toward ground zero. Returning water collided with falling ejecta and collapsing rock, building a thick geological record within hours. Scientists later drilled this deposit and found the first day of the Cenozoic preserved inside stone. A supersonic pressure wave raced outward, turning the atmosphere itself into a moving instrument of destruction. Many forests were flattened before they burned, stripped by winds stronger than the most violent storms. Thermal radiation reached exposed surfaces before the slower pressure wave and much of the falling debris. Near the crater, vegetation could ignite quickly. Farther away, fire depended on fuel, shelter, weather, and distance. The collision generated seismic shaking beyond ordinary earthquakes, sending waves through crust, oceans, and continental margins. Thousands of kilometers away, the ground could move before animals saw any debris from the impact. Shaking destabilized underwater slopes, triggering landslides that buried seafloor ecosystems beneath moving clouds of sediment. Even enclosed lakes and inland seas could oscillate violently as seismic energy crossed entire continental plates. Along some coasts, water withdrew first. What looked like escape was actually the warning of a much larger wave. The first regional waves carried trees, sediment, rock, and marine debris far beyond the former shoreline. The impact displaced an ocean. Its energy divided among coastlines, deep basins, narrow passages, and continental shelves. Models estimate vastly more tsunami energy than any historically recorded event, an ocean-scale disturbance without human comparison. In deep water, the tsunami might not resemble a towering wall. Its danger was hidden in speed and moving mass. As the tsunami entered shallow water, it slowed, compressed, and grew, concentrating distant impact energy against coastlines. Many coasts were struck repeatedly. Waves arrived, withdrew, and returned, rebuilding the shoreline after every surge. Powerful currents disturbed seafloor sediment, leaving geological traces even far from the crater. Impact-driven surges could travel inland and upstream, mixing marine debris with freshwater landscapes within minutes. Some distant deposits may record water surges occurring while impact glass was still falling. There was no single disaster front. Blast, earthquake, ejecta, and tsunami arrived in different orders. Within the first hour, one impact had become thousands of local catastrophes, shaped by geography and distance. The fastest ejecta now began returning from thousands of ballistic trajectories around the planet. Each returning fragment heated the atmosphere. Multiplied by immense quantities, that energy became a planetary concern. Across parts of Earth, the sky may have resembled a meteor storm generated by the planet itself. Re-entry heating varied with clouds, topography, water, and shelter. Exposure could determine immediate survival. Scientists debate how globally the heat ignited forests. Evidence supports widespread burning, not necessarily one simultaneous fire. Where forests burned, fire added soot to air, already overloaded with pulverized rock and impact gases. Shelter suddenly mattered more than strength. Water, soil, and small body size could buffer the first thermal assault. Open ground, forest canopies, and coastlines combined exposure to heat, debris, fire, and violent water. Cooling glass spherules fell worldwide, creating a thin time marker later recognized in rock. The first hours ended with a brutal reversal. After unbearable brightness, Earth began losing the sun. Vast atmospheric currents carried impact material around Earth. Within hours, the crisis crossed hemispheres. Heavy debris fell quickly. Fine dust, soot, and aerosols remained aloft and began controlling climate. As the atmospheric veil thickened, less sunlight reached the surface. Impact winter was beginning to assemble. Sulfur from the target rocks began forming reflective aerosols, although its total quantity remains debated. Fine silicate dust may have darkened Earth long enough to suppress photosynthesis on land and at sea. Soot added another dark layer, potentially intensifying the developing impact winter. Far from Yucatan, surviving animals faced a new threat: daylight fading without any local disaster. Photosynthesis did not stop everywhere instantly, but the energy entering food webs had already begun to fall. During the first day, darkness advanced faster than the full temperature collapse. Normal night crossed Earth. Behind it came a darkness that would not end with sunrise. While the atmosphere transformed above, the tsunami continued carrying impact energy through the Atlantic basin. Hours after impact, coastlines far from Mexico could still be struck by waves from an event they never witnessed. Continents blocked some paths and focused others. Distance alone did not determine tsunami danger. Around islands and peninsulas, waves bent, reflected, and interfered, producing locally extreme conditions. Even where coastlines escaped the highest water, deep currents could scour sediment and disturb seafloor habitats. The tsunami struck ecological bottlenecks: reefs, estuaries, nesting grounds, and coastal forests.
Marine ecosystems were physically damaged before climate effects fully arrived: turbulence, burial, and lost shallow water habitat.
The waves did not disappear after landfall. Reflections kept ocean currents disturbed long after the first arrivals. Survival now depended on location. Different habitats faced water, fire, debris, darkness, or combinations of all four. Where water receded, it left salt, sediment, debris, and buried food across landscapes that no longer resembled home. On Earth's far side, many large animals may still have been alive. Their world was already changing overhead. The first clues could be subtle: haze, falling grit, weakened light, unusual behavior, and spreading silence. Burrowing, aquatic habits, flexible diets, and small body size suddenly became powerful survival advantages. Food webs based on seeds, fungi, carrion, and detritus had temporary reserves when fresh plants failed. Freshwater systems offered shelter, stored organic matter, and temporary protection from heat, fire, and starvation. Large dinosaurs required abundant food, space, stable reproduction, and functioning ecosystems, exactly what the impact dismantled. Evidence suggests Northern Hemisphere spring, potentially striking many organisms during growth and reproduction. Ocean plankton still floated beneath the surface, but the sunlight supporting them was being filtered away. For some regions, the next sunrise arrived weak and distorted. Elsewhere, ordinary night simply deepened. Half a day after impact, Earth still rotated normally. Almost every surface system was behaving abnormally. planetary winds transformed a directional blast into an increasingly global atmospheric crisis. Heat, vapor, ash, smoke, and pressure disturbances created ingredients for violent, unfamiliar weather. Acidic precipitation added stress, although its timing and intensity varied across the planet. Local heat could persist even while Earth's broader energy balance turned toward rapid cooling. Every hour of reduced sunlight weakened primary production, beginning invisibly inside photosynthetic cells. Large herbivores did not need to die immediately. They only needed plants to stop recovering. Predators were one step farther from impact, but only one broken food link from starvation.
Impact gases changed seawater chemistry, adding chemical stress to darkness, turbulence, and disrupted food chains.
Extinction was selective, not random. Biology mattered, but shelter, diet, geography, and chance mattered too. Earth completed most of a rotation beneath the impact cloud. The new sky could persist for years. The first day did not kill everything. Pockets of life remained in water, soil, debris, and dormant tissues. Some dinosaurs probably survived the first day. Immediate survival was not long-term escape. For large animals, every remaining resource was finite: food, water, shelter, nesting space, and prey. Smaller survivors needed less food, hid more effectively, and used resources large specialists ignored. Seeds, spores, roots, and underground tissues could wait, while exposed forests could not. Deepwater organisms escaped fire and blast, but many still depended on food produced near the sunlit surface. As primary producers declined, extinction pressure climbed from microscopic cells toward the largest marine predators.
Flexible ecosystems could bend. Specialized ecosystems broke when one essential relationship disappeared.
By the 18th hour, spectacular violence was easing in many places. The quieter catastrophe was taking control. The disaster was changing from impact fight physics measured in seconds to ecological collapse measured in years. At ground zero, Chicxulub remained a furnace of fractured rock, hot water, debris, and unstable walls. Layer by layer, the crater recorded its first day. Melt below, chaotic debris above, then resurge sediment. Charcoal in the crater shows burning occurred quickly enough for fire debris to arrive during early sedimentation. The crater contains little sulfur-rich target rock, suggesting much of it escaped into the atmosphere. Worldwide, the same moment became a thin boundary containing impact glass, shocked minerals, soot, and extraterrestrial metal. After 24 hours, Earth still existed. Many organisms still breathed, but the old planet was already gone. The asteroid did not need to kill every dinosaur that day. It only needed to destroy their life support systems.
The decisive extinction unfolded later as darkness, cooling, chemical disruption, and starvation persisted.
One world dominated by non-avian dinosaurs was closing. Another was beginning among unlikely survivors. The first 24 hours did not complete the extinction. They created a world the dinosaurs could not rebuild.